Take out pen and paper. Okay, I'd like you to silently reflect. What is the difference between Math 3 and Math 1 and 2 that you feel, that you experience? From your experience, what is the difference between Math 3 and Math 1 and 2? Okay, discuss with the person next to you when you finish. Okay, let's hear a couple of people's quick opinions. What's the difference between Math 3 and Math 1 and 2 that you experience? Johan?
Content-wise, it's like lots of new things. And,
Which one?
Math 3.
Math 3.
Yeah.
Yeah?
Content-wise, it's different.
Oh.
Even though it's like the same pieces that you do, you have to put a lot more time in things. It's much harder to understand, and it takes much longer for you to actually do it.
I think that more new concepts in that one is you don't use the speed from math grid and lots of areas you haven't seen that ever before, like lower detected as small.
So that's the 1C to give you guys a few new bits. That's why 1C and 1D, sorry, 1A, B, and C differ. And the added sort of things like that's small stuff. This will give you guys something new.
I feel like when I'm trying to do that, and now, I'm seeing the results, I feel like I have to work now. So.
Yes, last one.
Math 3 is a lot about applying everything we learn quantitative. So it's application of all the techniques. It's all the regular problem.
Yeah. I'll take a stop there. Math 1 is sort of math for the masses. This is what they want everybody to have. They differentiate with A, B, and C, just so you guys don't do something too simplistic. But it's at the same level, the stuff that we added. Math 2 is sort of math for high school studies. Math 3 and 4 and 5 are purely university preparation courses. So that's why we have this sort of jump. And one thing I picked up on somebody said was it's far more theoretical. When you read the text, you have to understand it a lot better. It's not such just about the practical aspects of the procedures and solving the problems. It's an understanding the theory completely, which is really important. And they said that it takes longer to read the text, and then when you're doing the question, stand completely. And this is true. You have to change the way you approach your study. And you have to be able to understand that when I read this text and I do these questions, do I know it enough yet? Have I done enough? Or do I need to do more? And you have to regulate that yourself. And this is a progression. It's going to be a progression to university. And this year I'm preparing you guys for university studies in math and in other subjects as well. A lot of other subjects will have a large portion of math. Math is the biggest subject at university in Sweden. Most courses have math in them, which makes it the biggest. There's not as many candidates doing pure math. I'm not saying that. I'm saying that there's more candidates who are doing math when they're there. So what I want to focus on today is I'm going to give you a text to read, a university text, and we're going to read it. It is far more dense. It is far more dense than the text in the Origo book. But you're not far off that point. At the end of this year, you'll be moving into these texts. And when you hit these texts, you'll hit words that you've not seen before. It's not that I'm giving you a text and I'm jumping a bit. It was explained before. There'll be words that you haven't seen before. And you're like, oh, you have to be able to spot a word you haven't seen before and say, well, I need to look this one up. I want to fully understand it. I have to look it up for myself. And so we're going to have a read of this text. Before we do, I want to help you with that bit and give you a few bits and pieces, definitions for it. We talked yesterday about, so the notes I'm going to do in the next half hour, the theories or the knowledge I'm going to give you is non-essential knowledge. It's to help you read this text. The goal we're going for is that you should feel confident that you're ready to read a university level text in math. It's just a little bit different to what we do. It's a little bit slower, you have to read closer. That's the goal. So I'm going to explain things about a monotone function, what a monotone function is. The word's a good word to have. You can use it. It's a great word, and if you use this type of word well, there's opportunities in this course to use the word. It's a mathematical language, but you don't have to know it, is what I'm saying. Don't get overly worried that, okay, I've got to memorize all of this. We don't. We have to be able to get exposed to it and it not scare us. That's the goal. I can put it in front of you and you're like, okay, so it means that, right? I'm not scared of that. It's just a word. That's the goal. So we looked yesterday at the arithmetic laws for limits, finding the limit value. And that's the first thing it's going to talk about. It's going to mention reglerna for gränsfallen. And it sort of says, we saw this one yesterday, f plus g. We're talking about the arithmetic laws for limits. And it says, well, f plus g. What it means here is it's meaning that the limit as x approaches a of f of x plus g is equal to the limit as x approaches a of f plus the limit as x approaches a of g. And that's what this one's going to be. And we saw this one yesterday. You'll see a couple of others, but there's one symbol you all recognize, and it's this one. It doesn't say target. This means f of g. And what it means in this case is f of g of x, which I think we're familiar with. We call this a compound function, composite function. And it means that you first put in the value into the rule for g, and then you put the value into the rule for f. And we've done some of this type of function notation work. That's our first word. The next one I wanted to come across was no one reading this text, because this text is designed to run off a math 4, will know what hyperbolic functions are. But it mentions it's like and the hyperbolic functions. There's a family of functions called the hyperbolic functions. These are trigonometric functions. We don't need to know what they are necessarily. They're kind of funny functions. If I take the relationship x squared plus y squared equals 1, it draws a circle of unit length like this. So if we take that, and then if I add in the line y equals x and y equals minus x, I get like this. And the hyperbolic function, if we take that hyperbole,
X squared plus y squared is equal to 1.
oh, so that could go this way. We take a line like this, we can have a tangent here at this point, and then we can approach that line without ever touching it. We'll get a hyperbole like this. We get this curve. If we take a point here, like this, or we take any point on the curve, we draw the triangle like this, then this length here is the cos h, and this length here is sine h. So for any marked angle here, if you mark an angle here, if you imagine when you're here, it's going to be quite close. And as you increase the angle, you go shooting off in this direction, the point will. So this point here on the curve, any point on the curve is cos h, sine h. And it makes a set of values such that sine h of 0 is 0, so it's flat. And as we go up towards sine h of pi over 2, no, sorry, we haven't done that yet, 90 degrees, then it will go towards infinity. And this is just a function. It's like this. The next one is this word monotone. This bit's going to be interesting. Monotone. What monotone means is in a particular interval, the function is going in one direction. So for instance, a monotone function is always going up, or always flat, or always going down. So an example of a monotone function, I'll give you a couple of examples. An easy one would be this one. Y equals x cubed. It's monotone. It's always going up. It's always going up. We say strictly rising in this case. So this one is strictly rising. So because it's strictly rising, it's strictly monotone. It's always going up. An example of a function which isn't is this one. This is y is equal to x squared. It's not always going up. One period is going down. So you can talk about in the interval, x is less than 0, it's monotone, and in the interval, x is greater than 0, it's monotone, but for all x, it's not monotone. And that's what monotone means. What the function is going to talk about, what it's going to talk about is inverse functions, the opposite function of something. So this function here will have an inverse function. Be quite easy to find. What you do, you can't do it for this function. It doesn't have an easy inverse function because, as you can see, if we have this y value, then it's going to lead to two possible x values, which isn't a function. Whereas if you pick any y value on this, it will lead to one x value, which makes it easy to make an inverse function. We draw a line like this, and then it's a mirror reflection through this line. So it's going to be something like this. Or maybe not that. It's a mirror reflection down that red line. Like this. No. It's basically because if you put in a y value, you have to be able to get both x values out. Yeah, so and you can't. It's not functional. And it doesn't. So you're right. This function will reflect in the line y equals x and give the inverse function, which is why if we reflect it, it's going to look something like this, which is y is equal to the root of x.
So when come to mirror it, so again at the line and y equals 0. If you have so it's going to kind of on the other way down. Right. Slowing.
No, not quite.
So yeah, on the
Well, that's the vertical line. Can't be a single function. You have to have two functions. That's why we have the plus minus one to the deep order. It has two possible functions. So the other, because the other values are on that line down here that you're talking about, and it doesn't include the values over there as well.
yeah, okay, that depends.
Yeah. But whereas if you take a simple function which is monotone, then it's very easy to do. And quite a lot of functions are monotone. Those are the main words I wanted to cover. You're likely, when you encounter a text like this, is to not know what these three words were. And you have to look them up yourself a little bit, make sure you fully understand it. So I want you to read the first page up to example 11 on the second page. Okay? I want you to read it really slowly. I want you to read it really slowly and make sure you understand every line, because I'm going to have you explain what different lines here mean and what it's sort of telling us. We're going to have I think we've got time for at least 15 to 20 minutes to read one page. I don't want to take too long, so I'll stop at 15 minutes.
Då menar du folkgrejer? Mm. Ja, det är ju... Var och en. För det är the inverse.
Yeah, this is so this is one set. This is another set.
Så vänta, lång.
Just cannot set those assets. But that's an elementary. It's a discrete function. Okay, let's have a little discussion about it. Okay, explain to the person next to you what the first line means in your own words. What the hell does this mean? It calls line number 11. I det föregående up to the limits. First line. Explain with your groups. What does this line mean?
Jag fattar typ vad de menar, men samtidigt är
Okay, this first line basically says if we take a function, any function like this, which is made on an elementary function, we choose a particular point. This would have the coordinates x0, f of x0. Any point. The limit value here is the same as the function's value here, which means if we approach the function from that direction, and we approach it from that direction, and we evaluate it in that direction, they're all the same. We give an example of a function where this doesn't work. Let me take a function, f of x. So I have to use a function which isn't elementary, and you don't know it, but you do know this way of thinking of it. Let's say x is equal to that when x is not equal to 1, and it's equal to 2 when x is equal to 1. Make a function like this. This is a non-elementary function, it's a very simple function. When x is equal to 1, here there's a hole. And the function actually has a value here, 2. So the limit value of this function, so I take this function and I determine the limit as x approaches 1 of f of x, then the answer is 1. Then f of 1, the answer is 2. That's what this means. So it doesn't actually say much, it's just saying that in the previous chapter, we took a function that we used, that we recognize all elementary functions, this property is true. So in order to show an example wasn't, I had to use a non-elementary function. Everything else you've seen and know are elementary functions. Everything.
So that function is the grants by the f, or is it undefined?
It's 1. The limit value is 1. The limit value is the value that we approach, not that we get to.
Yeah.
So if we approach, and small amounts here, we're just slightly off this, we'll be approaching 1. Whereas if we take the value, we'll get 2. Obviously not. This function has to be not derivable when x equals 1, because it's not continuous when x equals 1. We've made this function not continuous by putting this point in here. We could make it continuous and derivable by putting this in. But like this, it's not. It's just giving a different value. Okay. What does line? Okay, the next line says that basically, if we take an elementary function f or g. Now, let's have let's see if you're getting the idea what an elementary function is. Can anyone give me an example of an elementary function? Let's have tons of examples. Hands up, did you? So y equals x squared. I'll just put the expression. I'll just put the expressions. Give me the expressions for elementary function. X squared plus 2 divided by x minus 2. This is not an elementary function. It's a rational function composed of elementary functions. This is a rational function composed of 2 elementary functions. The elementary functions are that one and that one. And then what this is saying across this line, the third one, f over g, is also going to be continuous because it's made of 2 elementary functions. So that's an elementary function, that's an elementary function. The other elementary, let's move, so all polynomial functions are elementary. All power functions are elementary. That is x to the alpha for all possible acceptable values for alpha. These are all elementary functions. So the square root function, 1 over x. This is great because this one brings in the polynomial, the 1 over x type things, the root of x type things. So all of that type of stuff fit into that one. And then any exponential function. This is where we have a to the x. All exponential functions. Do we know any other types of functions? That's what it is. Do we know any others? Trigonometric functions.
Where did you know that?
Math 1. You did. Okay. So all the trigonometric functions. Any others? We learned one this course. One more function. Absolute function. Can be like that. Can be like that. Have we come across any others? So these are all the elementary functions.
What about the logarithm?
Yep, elementary function. No. The logarithms, the elementary function is this one, and logarithm is the inverse of this one. So it's a family of inverse functions that we'll come to later, which is why here I'm not going into the Arcus functions, the inverse functions for these. So these are all elementary functions, and any combination of these, what this line is saying, any combination of these by adding them together, multiplying them, dividing one by the other, or putting one inside the other, will get you a continuous function. So all of these are continuous. Any combination of these using these laws, because it's all coming from the limit value. The idea that because what we need for a continuous function is the limit as x approaches a particular value for x, of f of x has to equal the value of the function at that point. This is our definition for a continuous function. The limit value has to equal the value of the point, and it's continuous. And in these functions, these functions are all continuous, and if you add them together using the laws of to do with limits, the limit when you add them together is the same as the limit for each one. It's basically saying this is continuous, so this has to be continuous. Yeah. Yeah, at the point of discontinuity. It's not defined. It's not in the domain. No. Technically, you should. When you specify a function, you create a function. We're a bit lax on it at high school. When you create a function, you should specify the domain always. And say this. Now, this is a continuous function with a point that's not in the domain. It's less clear when you don't specify the domain. Yeah. But this, to shorten it, I don't always specify the domain. If you're setting up these type of things, you have to say what the domain is and so on. Yeah. The inverse function of an elementary function. Okay. Line 12 is in italics. Explain to the person next to you in your own words what this line means. Explain to the person next to you what this line means. Continuous. What does this mean? Anyone? You were talking. Here we go.
Isn't that what you just said to Stan?
I don't know.
That if you
Can't remember that one. But
that logarithm function is the exact inverse of a continuous function.
Yeah.
Yeah.
Therefore, we know it to be continuous.
Yeah.
Let's have a go at a little look at inverse functions a little bit. Let's take the function f of x is equal to the cosine of x. What domain? We define the domain of this. What do we need to do to the domain to make that function strictly monotone? Do you know how that function looks? Right. Sorry, too much. We know the values of this. You get it out of the value table. Let me draw it a little bit more in the middle. Let me put the point 90 degrees, 180 degrees, 270 degrees, 360. Here the value is 1, here the value is 0, here the value is minus 1, here the value is 0, here the value is 1. This function looks like this. And it will look like this, where this is minus 90, minus 180, minus 270, minus 360, and it will continue. It's a wave function, which is why it's so beautiful and useful, because this happens a lot in nature when you're on a round planet surrounding a large round object with another round object rotating in a round pattern around you. A lot of circles in the physical forces, which generates a ton of things that follow this pattern. Okay, so this is a cosine function. Is it monotone? We want to make it monotone. What's the domain have to be? That would be true. You're cutting off this part of the graph. Okay, let's try and get all the possible output values. Let's say we want all the output of this, the range, goes from -1 to 1. So let's make a limited domain of of this function, which will have all the possible values in the range, from -1 to 1. Do you want to go?
From 0 to 1.
Let's take this. That function is strictly monotone, isn't it? So what's the domain? You can do that. So that would be a strictly monotone function. So we can create a inverse function to that. Means that the inverse function is going to have going to go to 1 and -1. Because this is 1 and this is -1. And when it's -1, the answer is 180 degrees. And when it's 1, the answer is 0. So it's going to end there. It's going to be 0 here. Not really good at this one. Should have been signed. Oh, sorry, I'm not quite drawing it right. Let me see. That's right, because that's not this. It looks like this. Okay. So what it's saying, what this line basically says, it says if a function is monotone and it's continuous, we know the inverse to be continuous. That's it. It means that if an inverse function is continuous, it would therefore imply that the other way around. But if a function is continuous, it doesn't always imply its inverse is continuous. If the function is not monotone.
For a function of the monotone, if it's not that it goes up there, then we would define it for all the areas where it goes down with a red base.
Yeah.
So for example, between
You could define monotone intervals.
yeah, but it doesn't have to. You can do it if we set to the same value. So no. On that one, if you define 360 to 180 also.
It wouldn't be monotone. It would have a monotone period and then another monotone period.
Okay, so it's not defined as it's going down.
No.
Yeah, overall.
Okay. The last bit here below line 12, it talks about the Arcus functions. What are the Arcus functions? It tells us that from this rule, line 12, all the elementary functions from polynomial to Arcus functions are continuous. What are the Arcus functions?
The inverse functions to sine.
Okay, are we listening? Lucas, what are the Arcus functions?
I don't know.
But Sana just told us perfect.
Yeah, I know. I'm sorry.
It's the inverse functions to all of the three trigonometric functions. So we know 3 and we know sine, which has the inverse function. So if f of x is equal to sine x, then the inverse function is arcus x. No, arc sine x with a limited domain.
Yeah, I was going to say that the arc sine function is also the function we use in that one to determine.
And that minus sign here to the -1 for a symbol for inverse function is why it's often referred to as this, meaning the inverse function. Okay. So all three of those are therefore continuous. These functions here are all strictly monotone and continuous. So these functions, these ones like exponentials, would be a function that might look like this. It's strictly monotone, very clearly, and it's continuous. Which means that the inverse to this has to be a continuous function. And because it's strictly monotone and continuous, we take this line here, y equals x. We can reflect this in that line, and we get something like this, which is y equals ln x, the log function. Looks like that. It's a reflection of that one in that line. So that's the inverse function to the log functions, and therefore they're continuous. That's what it says that one. There's a question on the last line of the first page. In pairs, try and work out the answer to this question. If it's corresponding value, then a reflection y equals x.
Är det typ som den här, där man visade en discontinuous när han hade...
No, you basically reflecting my value to use calculate.
Det här var 2 delar. Så att de satte som värde på... Alltså att om den går igenom och rik så sätter man bara...
This one's easier. But also
Men
if
det
we
är ju
take the
såklart mer
function,
komplicerat. Det finns kanske man kan sätta vilket som helst.
we take the function y equals x squared, where x is a member of x belongs to all of the x belongs to all of the, that means real values. That's the positive real values. So I'm intentionally limited. X is a member of the set of real, positive real. Yeah. X, I'm going to use the x squared away from 0. No. I didn't because I wanted to make it positive. So that's that function. And if we draw a line y equals x, that's the point 1, 1. That's through the line there. Then the inverse function is that. More or less. Yeah. I think that's true. Sometimes I can't think about it safely.
How about we add times we need to find a common factor. So then how about we do times 2 e to
Who needs help with this question? Who needs help? Anyone needing help? What did we get?
Okay, let's try to
Put this into your calculator and find the limit value.
So we're supposed to solve this.
What did we get?
Okay, so 2 e to x, that is when x is equal to 0, that is 2. Oh, it's just 2, that's
Why?
because you can do times.
Okay, let me help you get the answer to this question. If you have, and it has to be equal to the limit as x approaches 0 from the negative side of y1. So on your calculator, take y1 now on the home screen and put in 0.1. What do we get? $2.1 something. Okay. Put in y1.01. What do we get now? 2 point something or other? What value is it approaching? Because what we're doing now is this. When we're putting 0.1 and this, we're doing that. What value are we getting? We're getting, it goes towards 2. Now, on your home screen, put y1 minus 0.1. What do we get? 1.9 something? Put y1 minus 0.01. What are we going towards? We're going towards 2, but from the other direction. So this one here goes towards 2. Because these two are the same, it means that this one goes towards 2. And that's what the limit means. It means you have to go from both. We don't always check from both. Because we're always using elementary functions, which are continuous. Which is why you don't have to do it so often. So this goes towards 2, doesn't it? How could we make this continuous with no point of discontinuity? We just redefine it. We could define what this question is asking you to do is you do that investigation. So y1 can be redefined as y1 is equal to x is not equal to 0 and 2 x is equal to 0. And now it's continuous with no point of discontinuity. So you fixed the function, you've taken away the discontinuity point, made it completely continuous by a non-elementary function. This limit value that we're looking at, if you investigate the limit of that x, that's going to go towards 1, that's going to go towards 0. So this function inside the bracket is going to go towards 0. So sine x is going to go towards 0. This goes towards 0. So here we have an example of a limit value where 0 divided by 0 equals 2. Remember I said that 0 divided by 0 could be anything. Here's an example where 0 divided by 0 is equal to 2. Which is why we can't divide by 0. We have no idea what value it is. It doesn't approach infinity. We've often said that a number divided by 0 is going towards infinity. No, it can go anywhere. That's the bloody problem with it. In this case, 0 divided by 0 goes towards 2. There are other values that 0 divided by 0 will go towards. Very, very careful with that one. Okay, so I'm going to finish there at that point. I know I'm overrunning slightly. I'd like to ask one more question. I put up these questions for homework because I want you to read this text on your own without me explaining it. Now this is high school level. We read a page today of a university level text and it took us an hour to sort of get inside it. You have to read it a lot closer. how do you feel about, having read the first page, about your ability to read university level math texts? I will never be able to do it. I'm quite comfortable with it. It's hard, but I'm going to be able to get there, I feel. Hands up in your Wunderbar. Perfect. Threes. That's what we want. Threes. It's hard, but I can do this. And you can do it too. Okay? We're finished. Good.